Okay, welcome to Functions and Graphs Part 2. I wanted to start again with the definition that we just went over in Part 1. Remember, a function is a rule or correspondence that assigns to each element of one set exactly one element of a second set. So basically that's saying when we make a table, an equation, a graph, each x is only paired with one y. So I wanted to take a minute to explore that a little bit. There are a couple different ways that you can represent a function. One of them would be verbally. We could also do it, sometimes it's called numerically with a table. We could do it graphically with a graph, or we could do it symbolically with an equation. So when we represent a function verbally, there's two examples that I like to use. One I think I already went over in the first video, but that was when we relate a baby's age with a baby's weight, right? So usually at each age, which would be the x value, we take the baby to the doctor and the doctor weighs the baby, okay? And so with each age, there's associated one weight. Each x paired with one y, right? So that would be like a function. Another example I like to use is the idea of a UPC code, right? So when you go to the store, you pick up an item, you take it to the cashier, she scans the UPC code that's on the back, and the cash register pairs that code with one price. So each UPC code, which would be like an X, is paired with exactly one price, which would be like a Y. And I always like to point out that that is kind of a one-directional criteria. Right? So it doesn't really go the other way, by which I mean if we were to bring two items to the cashier, two different items, two different UPC codes, two different X values, but they happen to have the same price. She scans it, they both come up at the same price. That's okay. That is still a function because it doesn't really violate the criteria, which is that each X is paired with only one Y. Okay, so that's verbally, right? And we could talk about functions with words. Okay, another option would be using a table. So here's a couple examples that show a table. So you could take a second and copy these down if you want. What we're going to do with these tables, we want to answer the question, does the following table represent a function? Of course, we want to justify our answer, and then we want to list the domain and range and talk about what that looks like. So if we look at these two tables, take a second to look at those. Pause if you need to copy them down. Let's start with the first one. Is it a function? And I think yes, right? If we look at each x value is different here. So each of these x's is only paired with one y value. So we could say, yes, this is a function. And if you wanted to write down in words why it is a function, you could say pretty much the definition, right? Each x is paired with only one y. Okay, what about the second table? We could do the same kind of observations. We look at all the x's, right? And I think if you look carefully, there's one x value that's actually paired up with two different y values. These right here. Okay, so that causes a problem. That violates the criteria. So we would say, no, this is not a function. And if you wanted to describe in words why it is not a function, you could say something like the 2 is paired with both -3 and 4, right? And that violates the criteria for a function. Sometimes the books draw diagrams where each x is connected with its y by an arrow. So in that case, right, we'd have the same x paired with two different y's, and so in that scenario it is not a function. Okay, so let's add to this the idea of domain and range. For a table, it's kind of unique because all we have is what's listed in the table. We can't assume, even if there's a pattern, that the table continues. Right? We only have the information in the table. The nice thing about that is, usually if it's a table, it's a relatively small list of x values and y values. So when we write the domain and range, we can, in fact, list them out, right? So let's do that here. I'm going to use, okay, and so if we make a list for the domain, we said the domain is the set of all the x's, we can just list all the x values. And likewise for the range. When we list them out like this, we usually use these squiggle brackets. That's just the way that list notation is usually done. If you look in the book may list the numbers from smallest to largest. You're welcome to do that, but I don't make it a requirement. As long as they're all listed there, that's all I care about. Okay, even if it's not a function, we could still list the domain and range. And usually if there's a number that's repeated, we don't necessarily need to list it twice in our list of x values or y values. So really I only have to list the two once. If you list it twice, that's okay, but just know that that's kind of the convention, is to just list it once. Oops. Okay, so that's using a table. We can use a table to decide if something is a function, and we can make a list of the x values and y values for the domain and range. Alright, so the next possible way to represent a function is using a graph. And to test if a graph is a function, we usually use what's called the vertical line test. And so the vertical line test says if each vertical line intersects a graph in at most one point, then the graph is that of a function. So we can take a vertical line. I've drawn one here because I have a really hard time remembering which is horizontal and which is vertical. Vertical, like vertical blinds, is how I remember it. So we take a vertical line, pass it through our graph. If we can find even only one place where it touches twice, then it's not a function. But if every place where we would put this vertical line touches the graph in only one place, then it tests out. It's a function. Okay, so here's two examples of graphs. We kind of want to do the same thing. We want to answer the same questions. Does the following, I said table, but I meant graph. Does the following graph represent a function? Justify your answer. And we want to list the domain and range as well. Okay, so I put the equations up here really just as extra information. You don't really need that to answer the problem or the question being asked. But I know sometimes we see a graph and we feel like we need the equation for that graph. All right, so we could test these both using the vertical line test. Let's start with the first one. I think you could probably pass a line in lots of different places that would touch twice, right? So here's one possible place where we could pass a vertical line. And notice it's going to touch this graph in two places. So that means that this particular graph is not a function. Okay, the thing I didn't really realize when I learned this for the first time is that the vertical line test is essentially testing that each x is paired with only one y. So when the vertical line hits the graph twice, that means we have the same x value paired with two different y values, right? So this would be 2 comma, I don't know what these are, but 2.7 and 2 comma negative 2.7. So the same x but different y. And so we said in both ways that's not a function. Okay, the second graph here, I think you could look at a lot of different places, pass a vertical line, Here's one possibility, right? And it's only going to touch in one place every possible vertical line you could draw. So this one checks out. It is a function. Okay. And so to justify that, you could just use the vertical line test as your justification, right? It does not, or it does pass the vertical line test. And then we can list the domain and range. For the domain and range of a graph, there are infinitely many points on those curves we have for both of these graphs. So we cannot just list out the x's and the y's, right? And so that's where the interval notation becomes useful. So we want to use interval notation for domain and range. The domain is the x's, and the x's run from left to right. So when we look at the graph, we want to look, let me see if I can squeeze that in down here at the bottom. So the domain goes from left to right. And so if we look at, let's start with this first graph. We want to say, okay, is there a leftmost point? And there is right here. And that point is at the point 1, 0. So the leftmost x value would be 1. And do we have a rightmost point? Notice these arrows on the right hand side. So this sort of a sideways parabola is going to continue on to the right forever. So we're going from 1 on the left to infinity on the right. Now this graph includes this point. That's the leftmost point. So we're going to use the square bracket to show that the 1 is included. And I think we've said that the infinity always gets the round parentheses since it's not really a number. It's kind of more of an idea. Okay, so that's the domain. The range is the y values, and the y values are vertical, so they go from bottom to top. So when we look on the graph, we want to kind of make the same judgments based on the bottom and the top. So we look and say, does this graph have a lowest point? And because this arrow continues down as it goes to the right, it does not, right? So it's going to go all the way down to negative infinity. Does it have a topmost point? For this graph, it does not. Same reason as this top branch goes to the right, it's going to continue up as well. So for the range, all the y values are covered. It's going to go all the way down to negative infinity for that bottom branch and all the way up to positive infinity for the top branch. Okay, we could make the same kind of analysis of graph number 2. Alright, so we look at it from left to right. On the left, this left side is going to continue left as it goes down. So it doesn't have a leftmost point, continues to negative infinity. On the right, this branch on the right is going to continue to the right all the way as it goes down. So the domain is going to include all real numbers. So from negative infinity to infinity, it stretches all the way out. Okay, and then the range, again, from bottom to top, the arrows are going down, so it does not have a lowest point, but I think we can agree that it has a highest point right here at the point 2, 4. And this is the range, so we're referencing the y value. So we're going from negative infinity at the bottom up to 4 at the top. And because that point is included, we want to use a square bracket just to show that it's included. Okay, so this is a skill that's going to take some practice. So take some practice, take some time looking at graphs and practicing writing down their domain and range using interval notation. Alright, so that's what a function looks like when it's a graph. The last thing we want to talk about is symbolically, when it's written as an equation. Okay, so when we use an equation, I'm not going to ask you if an equation is a function. Right? Usually the best indication is if there's a plus or minus included there. It's not a function in that case. But otherwise, we're not really going to be tested on that. We are, however, going to talk about the domain of a function when it's written as an equation. So some things you want to think about when you're talking about domain. Remember, the domain includes all of the real number x values that produce real number y values. So I want to think, okay, what x is going to allow me to get a real number out for y, and maybe the opposite of that, what x is going to make y undefined, because those are the x's I do not want to include in my domain. There's two really common restrictions that are going to come about, and for the most part of our class, we'll add one maybe at the end, I think, when we talk about logarithms, but for right now we have two. So the denominator of a fraction cannot equal 0, and that's because we can't divide by 0. You try it with your calculator, it doesn't work. Okay. And then the second common restriction is that the argument of a square root must be non-negative. Right? I can't take a square root of a negative number. So I can take the square root of 0 and anything positive. I can use my calculator for the ones I can't do in my head, but I can't take the square root of a negative. Okay, so we can apply those two restrictions to these functions. They're kind of examples of these. The directions say find the domain, write your answer using interval notation. Okay, so for the first example, we have y equal to the square root of x minus 2. And we're going to use this idea that the argument, which is the x minus 2 on the inside, must be non-negative. So you could think about what kind of x's are going to work. Right? Whatever x value makes this inside part 0 is kind of the dividing line between numbers that work and numbers that don't work. In this case, that's 2. I think you can pick up on that pretty simply, right? So if I put a 2 in here, 2 minus 2 will be 0. So that's 2 is the dividing line. So then we have to figure out, all right, is it numbers bigger than 2 or numbers smaller than 2? You could test some things out. All right, so you could do some of that in your head. The easiest way to write it out on paper is to take the argument and make it non-negative or positive, greater than or equal to 0. And then work that out. Get x by itself, add your 2 over to the other side. Essentially, this is your domain. So any number 2 or bigger, right, greater than or equal to 2, is going to work in this function, and it's part of the domain. So then my next step is to write that in interval notation. So if you need help doing that, the number line is a really good visual aid. It's not the answer, but it is a good help. So we're talking about numbers that are greater than or equal to 2. Because of the equals, I'm going to fill in the dot, and because of the greater than, I'm going to shade to the right. And then I can write my interval notation from there. Because the equals bar here means that the 2 is included, I'm going to use the square bracket, and I'm going to list the endpoints from left to right. Okay, so there's our domain for the square root example here. And then the last one is a fraction. And so above, we said that the denominator of a fraction cannot equal 0. You can probably pretty much eyeball this one. There's not a whole lot of working out. You could probably do it in your head. But if you wanted to work it out, we want to say, okay, remember the denominator cannot be 0. So I can isolate the denominator and say, okay, well, what does that mean for my x values? If I work it out and I get x by itself, that means that x cannot be 7. Okay, so again, you could probably do that part in your head. Then the next part is to write that set of numbers, all the other numbers but 7, in interval notation. So here's my number line as my visual aid, right? So if it's not equal to 7, it could be any other number. It could be all the numbers smaller than 7 or all the numbers greater than 7. And this breaks the number line up into 2 parts, and I want to write both parts in interval notation. So I'm going to go from left to right, So from negative infinity up to 7. But I don't want to include 7, right? Because that's the whole point of this. So I'm going to use the round parentheses. That means technically I'm going up to 6.99999. Okay, and then on the other side, round parentheses again, so that I start just after 7, 7.00001, and I go all the way up to infinity after that. If there's more than one part to my interval notation like this, I usually put a union in the middle because that joins them together into one set. All right, very good. Well, that kind of summarizes a lot of what we're going to work with in terms of functions and its definition. So I hope that this gave you a good explanation of each of these and that you'll take some time to practice each one a little bit. Good luck. Great. Thank you.